Well, it's great to be here. Actually, as a journalist and not an author, I wish I could go to every session. And I was just wandering around, and the kind of work you're doing is fascinating, and I'll talk about how it might relate. But I think, you know, I was thinking about this on the way out here on the plane ride from New Jersey, that everybody here is looking forward. You're thinking about this industry, where it goes, what's in the pipeline. So here's this guy talking about Bell Labs, the great bastion of research and development in the 20th century. So what in the world is that going to tell me? Why do I have to think about the past rather than the future? And I think there are two answers to that real quick before I jump in and talk about Bell Labs. And the first, I think, is that, you know, just in terms of knowing where the technologies that you rely on came from, there's probably no better place to look at than Bell Labs. This is really the place where systems engineering was created in the 30s, 40s, 50s, and 60s. All of those, platform innovations upon which industries were built, the transistor, the laser, the ideas behind digital communications, communication satellites, Unix, the C programming language, all originated in this one laboratory over the course of several decades. I think the second part of that answer about why it matters, though, is a little different. And that's that, on the one hand, Bell Labs is a really great ecosystem, I think, in terms of looking at how a regulated public-private partnership worked in a very fruitful and innovative way, really over the course of 75 years, depending on how you want to define Bell Labs' golden age. And I think the second part is that I'll tell a couple stories of innovation about Bell Labs. I mean, my book is filled with many stories about how so many of those technologies I just listed came to be. But when we hear about these stories about how the transistor was invented, for instance, and how long it took to develop, I think we get some kind of timeless understanding in many ways of how innovation works, what kind of ingredients precede innovations, how it differs from invention, how it can impact society, and really what it takes for that to happen. So with that in mind, let me just kind of back up. Actually, I think we have to all kind of go back in time to sort of get a handle on what this place was. And probably there's no better place to begin than 1877, when Alexander Graham Bell patented the telephone. Even back then, there were patent fights. As many people know, that there was another guy who had a patent for the phone at about the same time. It was granted to Bell. And what happened in the wake of it was the company that sprung up around Bell's invention, American Telephone and Telegraph, really by the turning point of that century, by the early 1900s, was on its way to really becoming the largest company in the world. And if we tune in around 1915, 1920, AT&T was the largest company in the world by assets, the largest company in the world by valuation, the largest company in the world by number of employees. And AT&T wasn't just one company. It was a multitude of companies under one umbrella. Its connection with the consumer were these local operating companies. And AT&T owned either all or part of 23 companies that offered local service. Pacific Bell, for instance, Southwestern Bell, New York Telephone, again, owned all or part by AT&T. AT&T controlled one of the largest manufacturing companies in the world, which was Western Electric. Again, a vertically integrated company where everything was built within that corporate structure, everything from the switches that connected callers to the leather harness belts that held the linemen up to the phone lines. These were manufactured at Western Electric. AT&T controlled 80 to 90% of the phone service in the United States, but it controlled all of the long-distance service through an entity called AT&T Long Lines. And I think finally, for my purposes, for our purposes today, in 1925, this mammoth phone company decided it was going to consolidate all of its engineering and science into one entity. It was going to create a laboratory. They called it Bell Telephone Laboratories. The first actual building was on West Street in Greenwich Village. It's still there today, actually, but like a lot of things in Manhattan, it's been turned into apartments. But it was really taking the industrial laboratory to a new scale. Industrial labs had been built before, for instance, in some of the pharmaceutical concerns in Germany. But really, this was an entity of 2,500 to 3,000 people, and it had a kind of dual purpose. It had a very large core of engineers who were there to solve the near-term problems of the phone system and for those regional Bell telephone companies I talked about. It also had a core of researchers within it, scientists who were really looking for new knowledge, who were thinking about the long term, who were thinking about what human communications could be or should be. And this kind of short-term, mid-term, and long-term thinking really came together in a quite remarkable way. So I think that being part of the phone company, being part of this monopoly, AT&T had no competitors. It could really think long-term. It didn't have that quarterly profits burden. It didn't have the competition nipping at its heels. And being the laboratory for this company was a tremendous advantage. You could think long-term. You had a tremendous revenue stream to tap into. But even so, I don't think the success of this place was preordained. And I actually think that it really took a small group of visionaries to make this place work. And in the book, the central figure, I think, for Bell Labs, and I think he's the central figure of my story, and maybe a very underappreciated figure in 20th century innovation, is this fellow Mervyn Kelly. Like a lot of people who came to Bell Labs, Kelly grew up poor in western Missouri. His father tended a hardware store. He went to a local school. A teacher kind of identified a knack for mathematics and physics. Kelly decided to get a PhD in physics when really there were only about 100 physicists in all of the United States in 1915. And in the University of Chicago, he got a PhD, and one day a recruiter for the phone company came through and hired this guy, and Mervyn Kelly came east to work for the phone company. Now, this is a guy with tremendous insight. I wouldn't call him a brilliant researcher. He was a brilliant manager, almost kind of congenitally. Somebody with a knack for that, somebody with tremendous energy, somebody who ran up and down staircases. And by 1925, Mervyn Kelly was working at Bell Labs, and he was a middle manager in what was then called the Tube Shop. It was a small industrial shop, part of Bell Labs, in Lower Manhattan, in Lower Greenwich Village, and Kelly was making these things. He was making something called the 101D. It was a vacuum tube. It was about the size of an incandescent bulb. And as you can see, it looks sort of like an incandescent bulb. For those of you who know well this sort of technology that is almost dead, this was something that could repeat or amplify phone calls or could switch circuits very quickly. Actually, Kelly was really good at running the tube shop, managing this shop, and he considered this invention, which was really then about 10 years old, the vacuum tube, as the miraculous innovation of his time. What it really did is it made cross-country phone service possible because phone signals were weak, they would attenuate. If you tried to send a phone call from New York to California, you could not do it. You could try different tricks and engineering tricks and mechanical engineering tricks, but the phone signal would die out either around Chicago or Denver. But this changed everything. What it did was it gave you a high fidelity boost to the phone signal. And the phone company eventually created repeater stations every 100 miles. And a phone call traveling from New York to San Francisco would go through these repeater stations. The signal would be boosted by this 101D bulb, and it would be pushed farther and farther along the line. And voila, we had long distance, high fidelity service. As I said, Kelly was really good at making these things, and during the course of his management tenure in the tube shop, he made them better and better. In fact, he came to see innovation very simply as the job of making something better or cheaper or both. And he increased the life of this thing by something like 60,000 hours and its durability. And he began to think, he's very good at, I guess, what we might call incremental innovation. But he began to see that this was actually an inherently flawed technology. In fact, he would go home to his wife, he was living in the Bronx at the time, and he would complain and he would say, I wish something else would come along that would replace these things. They were rather large for a kind of inherent electronic element. They used tremendous amounts of power. They had to run all the time. They had to run hot. They gave off tremendous amounts of heat. And they broke all the time, actually. Even though he increased durability, he was always throwing them out in the shop for quality control reasons. Again, an inherently important technology, an inherently flawed technology. There was nothing in the pipeline at Bell Labs or in telecommunications at the time that could replace these things. And as the 1920s wore on and the 1930s, they became more and more a part of that structure of the phone system. Kelly, in turn, kept getting promoted to the point where he became the chief of research at Bell Labs. And by the late 1930s, in fact, by about 1937, Kelly is really the boss at this point. He's on his way to becoming the president of Bell Labs, and he's deep into the structure of science and technology of America. He becomes an advisor to important people in Washington. But at that point in time, late 1930s, as chief of research for Bell Labs, he is walking down the hall one day, and I have this kind of fascination as I began my research in my book, and still as a journalist, of how do actually huge, momentous innovations occur? You know, when the world really kind of almost turns on its axis. And sometimes I think it's almost serendipitous if you're in the right place at the right time with the right people. Mervyn Kelly had a best friend at Bell Labs. His name was Clinton Davisson. He won a Nobel Prize. He was kind of this archetypal Bell Labs researcher. Didn't want any part of management. He just wanted to do research all the time. Well, one day, Kelly's walking down the hall to go visit Davisson, his friend. Davisson's not in his office that day, but another guy who Davisson just started sharing an office with is there that day. And his name is Bill Shockley. Kelly had just hired him the year before from MIT. He's an utterly brilliant physicist. And that day, for whatever reason, Mervyn Kelly decides to give Bill Shockley a lecture. And he tells Shockley that he wishes he could get all of the switches out of the phone system, that we need some kind of technology to replace them. So I talked about getting the tube. The tubes were this inherently flawed amplification technology in the phone system. Well, that day Kelly's talking about switches. These are these relay switches. They're electromagnetic. There are millions of them in all these switching centers in every city in the country. They click open and click close to connect callers. They are proliferating at a tremendous rate as the traffic increases in the phone system, and they wear out all the time. They're a tremendous expense. For reasons some people in the audience probably know, switching amplification can be related. Maybe if you come up with a replacement for a switch, you also might have a replacement for an amplifier. And that day, when Kelly tells Shockley, can we do something without moving parts, a replacement for a switch, something electronic, something that doesn't break, something that doesn't use a lot of power, Shockley remembers this for the rest of his life as the day Dr. Kelly stopped by his office to give him a talk about getting all the switches out of the system. Actually, Shockley goes to work on this right away. He tries to build a kind of electronic amplifier or switch. He starts using this new class of materials that some of the guys at Bell Labs are tinkering with down in South Jersey. They're called semiconductors. He starts using silicon, germanium. Actually, Shockley focuses on copper oxide. The problem with Bill Shockley is that he's a really good theoretical physicist, but he's a horrible experimentalist. And he fails over and over again. He brings in some other experimentalists at Bell Labs to try and help him out, and they get nowhere. They keep working on this through the late 30s, but really by the 1940s, early 40s, all this work stops. And it doesn't stop necessarily because they're failing, although I think failure is an underappreciated ingredient in this whole story. It stops because the war comes, and all the research and all the long-term thinking at Bell Labs is really directed towards focusing on wartime technologies. Mervyn Kelly actually focuses on how Bell Labs can aid the war effort. A lot of the people at Bell Labs start working on radar, and actually the radar systems that they use start tapping semiconducting materials. They use germanium and silicon crystals, which become crucial to this technology, and actually they start to understand a lot more about semiconductors in the process. But as the war starts winding down, as victory is in sight in 1944, Mervyn Kelly, now the vice president of Bell Labs, the executive vice president, he's in charge of day-to-day operations, begins to start thinking ahead to what this organization could be. And actually, he writes a long memo. He looks ahead, and he writes a memo about what the future of post-war electronics will be. He decides that Bell Labs has to lead, can lead. He sees a kind of era of competition unlike anything that came before. He sees that this new class of materials, semiconductors, holds great promise. And he decides that he's going to create a team at Bell Labs. Actually goes down to Washington where Bill Shockley's working, says, come back up, I want you to run a team to look into the deeper nature of semiconductors. This team's kind of interesting, actually, and it sounds so obvious today, but at the time it was not. Kelly, during war, had gained a keen appreciation for how interdisciplinary teams can do things that, that like-minded people cannot, that you want a certain tension between people, that really new ideas come from the interface sometimes of different disciplines and not necessarily two physicists or chemists talking with each other. So this team that he really handpicks under Bill Shockley contains physicists, both theoretical and experimental, chemists, metallurgists, electrical engineers, and all sorts of other technicians from Bell Labs, really to collaborate to understand what semiconductors are and to think deeper about whether there might be some kind of invention for the phone system. In the back of their minds, everybody who's working on this project believes that they may, if they're fortunate, come up with some kind of replacement for the vacuum tube, some kind of new amplifier. Well, they begin working in earnest actually in the summer of 1945, and they fail right away. They fail again. One of the guys on the team says, you know, it's like we're groping in the dark. And really, a year goes by, and 2 years go by. And then in the fall of 1947, two physicists on this team under Shockley, Walter Brattain and John Bardeen, come up with, I'm sorry, they're working in New Jersey at this point, apologies for that, and Murray Hill. They've moved out of New York. But the two physicists, Bardeen and Brattain, come up with the first transistor. I don't know if anyone's ever seen this. It's about the size of the tip of my pinky. It's actually on display in New Jersey at the old Bell Labs facility. And what they find, what Bardeen and Brattain find, is that if they pass a voice signal through this, it can amplify their voice 18 times. And really, it's that slice of germanium under that arrowhead. It's a slightly impure slice of germanium. The word doping isn't really known yet at the time. The semiconductor industry does not exist. But this thing, this transistor, as they named it, it was almost named the Iotatron. Thankfully, it was not. Transistor won in a poll of people at Bell Labs. Becomes this sort of new and miraculous device. Why does this thing matter? Well, they realize right away that you can fit 100 of them in your outstretched hand. They don't yet know that you'll be able to fit millions of them or billions of them on the size of your thumbnail. There's no idea of that. But they understand that the miniaturization of electronics is hearkened in by this invention, that this is an incredibly low-power device and conceivably very tiny. And I think that the issue they face immediately is they find that these are really hard to make. And they start grappling with that kind of research versus development transition. And to actually, I think it speaks to that difference between invention and innovation. I'm a great believer that research is sometimes overestimated and development is chronically underestimated. And this is indeed what they find at Bell Labs. And it really takes, I think, about 4 or 5 years until they start to create kind of processes to manufacture these. They build a manufacturing facility in Allentown, Pennsylvania. And that's about when it's going to make a kind of impact on culture, when I think we can say it's not just an invention, but it's something that's going to be manufactured at mass scale and have an impact on society. It's going to be an innovation. And I just want to point out the time frames here. So if we went back to 1925, when Mervyn Kelly's first frustrated with tubes, to about 1954, 1955, to where the transistor, this dream of his that fulfills this problem, is really going to enter society, we're now at about 30 years. And that doesn't even include the advances in quantum mechanics that preceded the invention. So really, we're talking very long time frames for these kinds of breakthroughs, and I think even longer, too, as you'll see in a second when I talk about how long it actually took before it made a bigger impact in the culture that we know today. At about the same time, actually, that this is going to be mass manufactured, in the very same lab that, that the transistor was invented, 3 guys are working on a very different technology at Bell Labs. And there's a fellow named Cal Fuller who's a chemist, and he's making these very deliberate, impure slices of silicon in his kiln. And he's giving them to a physicist named Gerald Pearson, who works actually in another building, and Pearson is testing them. They're trying to build something called a silicon power rectifier, which I won't go into here, because Pearson actually starts testing these silicon pieces and finds that they have an incredible photoelectric effect. They generate more electricity when the light is shined on them than anything in the scientific literature says they should or could. And this strikes Pearson. The other thing that strikes Pearson is that he has a friend in another building. This is kind of a good example of the Bell Labs ecosystem, whose name is Daryl Chapin, and he's an engineer. And Chapin has been asked by the Bell Labs executives to come up with power sources for remote repeater stations. Those were those repeater stations where phone calls were amplified. Sometimes those repeater stations were really out in the middle of nowhere. They weren't on the grid. They used diesel generators or dry cell batteries. And the brass at Bell Labs had wondered whether there was some other power source, wind power, something atomic or nuclear, that could power these stations. Pearson wonders to Chapin and brings in Fuller and asks if they can use the power of the sun and maybe these silicon panels that they're using to try and power these repeater stations. The three men get together. They all work in different buildings, but kind of serendipitously over the course of about 9 months, they come up with the Bell Solar Battery. It's the first silicon solar panel. It's the ancestor of every photovoltaic panel in the world. And they actually tested out in 1955 in Americus, Georgia, at a repeater station. It's the first solar installation. It actually works splendidly. They generate enough power to run this repeater station. It has other problems of economics, which I'll talk about in a second, but in terms of its efficacy, it's a fabulous success. So again, just two stories from Bell Labs, but I think they're kind of emblematic in some ways of some larger principles of innovation that I think might be helpful or might be food for thought. What do we learn? I mean, I think for me, one thing that's so clear here is that that this was, as Arno Penzias told me when I interviewed him, who's a Nobel laureate, that this was a problem-rich environment, that at Bell Labs, it wasn't so much that they thought of innovation as a response to good ideas, but that they thought of innovation as a response to really good problems. And I don't think that was just a semantic difference. I think it was fundamental to how they did it. Fortunately, they were in an industry that was ever expanding. There was incredible amounts of phone traffic and data traffic, and that question of can we satisfy these problems incrementally, can we manage the phone traffic, or do we need to do something discontinuous, something that is a breakthrough technology like the transistor. Again, the transistor was that response to a problem. How are we going to get the vacuum tubes or switches out of the system? And I think the solar cell, too, was a response to a different kind of problem, but a similar one. How do we actually find power sources for these repeater stations? So again, good problems, good innovations. Ideas, everybody has ideas. Second, I think that we're not very good at perceiving the future value of today's breakthroughs, and I think that goes for what was going on back then too. Actually, when the transistor was unveiled, it was on the back page of the New York Times. Here he is, the greatest invention of the 20th century. It was buried in a column in the culture section called The News of Radio. They said that these guys at Bell Labs have this thing that will replace vacuum tubes. And it's really, they couldn't understand the value. Many of the people at Bell Labs understood the value, but in terms of the general culture, it was completely unproven and not understood at all. The solar cell was actually the exact opposite. The solar cell was on the front page of every newspaper in the country. We'd reached a pivotal juncture where energy was going to be plentiful, free, possibly, and that we were never going to run out. And of course, we kind of got these backwards. And we got them backwards because of the economics, I think. That the transistor, the cost curve for the transistor came down dramatically, very rapidly. And then in those early days, it was kept alive by the defense industry, which saw great advantages in buying transistors, which were still more expensive than vacuum tubes. But buying transistors for airplanes and submarines where that premium product had great value anyway, where space and electricity were constrained. But the solar cell, and I might just add, and eventually the guys in Texas and California figured you could jam thousands and millions and billions of transistors on a chip, and then their cost became a fraction of a penny. But the solar cell, of course, has never really enjoyed such dramatic drops, and only now, really about 60, 70 years after its invention, is it starting to approach grid parity with fossil fuels. And I think those lengths of time are instructive. But again, we see that the economics, just how crucial it really is right here. Third, that even when we think we understand the value of breakthroughs, maybe we don't. Early on, the transistor was seen as a replacement for the vacuum tube. And it was, but really its greatest use, I think, has been on microprocessor chips and as the essential part of our computers and cell phones today. And really at the time, very, very few people saw this. Mervyn Kelly on the 5th anniversary of the Transistor says, no one can see where this will lead. And he's right. He believes it'll lead great places, but he has no idea where. And as I was digging through the archives when I was researching my book, really only one person wrote to Bell Labs, to the executives, requesting a sample of the transistor. It was a guy named Jay Forrester. He was a professor of engineering at MIT, and he said, can you send me a couple of those, because I think they have great value in this computer apparatus I'm building. Actually called a high-speed computing apparatus, which I don't know how high-speed it was, but it was 1948. But I think just how insightful that was, but also the Bell Labs guys sent Forrester one right away, but how difficult it was to perceive its uses. Fourth, and I think really, this is one reason why I've told the stories of the transistor and the solar cell, is because we see that revolutionary breakthroughs and platform innovations can kind of be integrated together, can combine and recombine into what I talked about with Forrester too, into innovations that I think can't possibly be predicted. And just listening a little bit today and walking around, I think this is especially poignant now as we start to see the commercialization probably of so much theoretical and foundational work on space and space travel. And I think there are analogies too with a telecommunications industry that was at one point deregulated and moved from a kind of complete kind of government oversight to a very competitive industry here with the space industry too. That just as communications went from local service to long distance service to intercontinental service to radio telephone service to cellular service to now having Android computers in our pocket, that something like an inflection point happened then, and I wonder too if maybe it's happening now too with your industry. But certainly that relevance is there, at least for me, in the way I see it. And I do know, too, that that's a picture of Telstar, by the way, which integrated a tremendous number of Bell Labs innovations, transistors, all sorts. I think the final count was something like 16. Some of them were off-the-shelf technologies, which never were intended to be in any kind of satellite communications effort. It wasn't even conceivable, and those are the black plates are very early silicon cells there. But again, that kind of integration, the parts, the whole greater than the parts, and the combinations and recombinations being unforeseeable really stands to something to be thought about. And while I know too that while these examples, the transistor and the solar cell, Telstar,